Have you ever stopped to think about what's actually happening when you send an email or stream a movie? You're using a hidden language, you know? It's this secret code that lets our computers, our phones, all our devices talk to each other through miles of cable or even just through thin air. So today, let's pull back the curtain and take a look at the secret language of data. It really all comes down to one simple sounding question. How does a 1 actually travel through a wire? I mean, we talk about data being ones and zeros all the time, but a 1 isn't a physical thing, right? You can't just, stuff the number 1 into an Ethernet cable and hope for the best. So how does it really get from your computer to, say, your router? Well, the answer is translation. Our raw data, those conceptual ones and zeros, they need a translator. We have to convert the idea of a 1 or a 0 into something physical, an actual electrical pulse or a radio wave. This is the story of how we teach data to speak the language of whatever medium it's about to travel through.
Okay, so let's start with the most common scenario, what I like to call the digital highway. This is where we're sending our digital bits over a physical digital medium, like that trusty old cable connecting your computer to the internet.
The set of rules for this translation is called line coding, and you can really just think of it as basic grammar. It's an agreement that says, okay, everyone, this specific voltage level is how we say 1, and this other voltage level is how we say 0. Simple as that.
Now, one of the most straightforward types of grammar is something called polar encoding. The rule here could not be simpler. We'll use a positive voltage, maybe plus 5 volts, to represent a 1, and a negative voltage, minus 5 volts, to represent a 0. Positive for 1, negative for 0. Got it?
And you can see that translation right here in action. A 1 goes up, a 0 goes down. But here's where we hit our first snag. What happens if you have to send a long string of 1s or a long string of 0s? The signal just flatlines, and for the receiver on the other end, that's a huge problem. Its internal clock can start to drift, and it can totally lose track of where one bit ends and the next one begins. It loses synchronization. So, of course, engineers came up with a really clever solution called bipolar encoding. This one uses 3 voltage levels. A 0 is just 0 volts, nothing. But here's the really cool part. Every time we send a 1, we alternate the voltage. So the first one is positive, the next one is negative, the one after that is positive again, and so on.
And this little trick is brilliant for a couple of reasons. First, that constant switching for the 1s keeps the receiver's clock perfectly in sync. But even better, if the receiver ever sees 2 positive pulses in a row or 2 negative ones, it knows immediately that an error has happened. So we get synchronization and error detection baked right in. Pretty smart.
Then there's another really cool technique, Manchester encoding, which is kind of the secret sauce to self-synchronization. Now, with this method, the actual voltage level, whether it's high or low, doesn't really matter. What matters is the transition that happens right in the middle of the bit's time slot. A switch from low to high might mean 0, and a switch from high to low could mean 1. And because every single bit has a transition, the receiver can never, ever lose sync. This is why it was so reliable for early Ethernet.
So here's a quick cheat sheet to pull it all together. Polar encoding is super simple, but it has those sync problems. Bipolar is much better, but it can still get tripped up by a really long string of zeros. And Manchester is fantastic for staying in sync, but, and this is a big but, all those constant transitions mean it takes up twice the bandwidth. As always, there's no perfect solution. It's all about trade-offs.
So we've got our grammar sorted out, but what happens if the data itself, the actual message we're trying to send, is the problem? What if you genuinely need to send, say, 1 million zeros all in a row? Even our clever bipolar encoding would struggle with that.
Well, this is where an even more advanced technique comes into play. Just imagine this for a second. You have 4 bits of data that you need to send. They go into a special encoder. And what actually comes out the other side, ready to be sent down the wire, is a 5-bit code. Now, you might be thinking, wait a minute, why on earth would we add an extra bit? That sounds totally inefficient.
This technique is called block coding, and honestly, the best way to think about it is like a spell checker for your data stream. We take a block of data, say 4 bits, and we map it to a slightly larger block, like 5 bits. The whole point is to pre-translate any problematic bit patterns into safe ones that we know won't cause sync issues. And here is a perfect example. It's called 4B/5B, and it's used in things like fast Ethernet. Just look at that first line. If we needed to send the data 0000, 4 zeros in a row,
That could cause a problem. But with block coding, before it even touches the wire, it gets translated into 11110. We've cleverly replaced a bad pattern with a good one that has plenty of transitions, all for the low cost of just one extra.
Okay, so we've pretty much mastered the language of the wire. But what about the air? What happens when there is no wire? The principles are actually quite similar, but the medium is totally different. We're not controlling voltage in a cable anymore. Now we have to manipulate invisible waves traveling through the atmosphere for stuff like Wi-Fi or a phone's cellular signal.
So instead of sending distinct voltage levels, we have to make our data piggyback on a continuous analog carrier wave. This whole process is called modulation. And as you can see, there are a few basic ways to do it. We can change the wave's height, its amplitude. You can think of that as shouting for a 1 and whispering for a 0. We can change its speed or its frequency, a fast wave for a 1, a slow wave for a 0. Or we can shift its starting point, which is called its phase. Modern systems like Wi-Fi actually use really complex combinations of all of these to cram as much data as possible into the signal.
All right, on to our final scenario. What if the source of our information isn't digital at all? I mean, how do we take something from the real analog world, like the sound of my voice right now, and turn it into the ones and zeros needed for a Zoom call? This conversion process is called digitization. The very first step is to sample the continuous sound wave. What that really means is we measure its height or its amplitude thousands and thousands of times every single second. This creates a series of little snapshots, almost like a flip book that animates the sound.
Okay, next, each one of those tiny snapshots is quantized. This just means we round its value to the nearest level on a predefined scale. It's kind of like taking an exact measurement and rounding it to the nearest inch. The more levels we have on our scale, the better the audio quality will be, but the more data it's going to take up.
And then, the final step, we encode those levels into binary. Each level on our scale is given its own unique string of ones and zeros. And just like that, the sound of a voice has been perfectly translated into digital data that a computer can understand and send anywhere in the world.
So, as we start to wrap up here, let's just bring this all back together. What we've really been exploring this whole time is this incredible, unseen language of data transmission. All the essential translations that make our modern digital world even possible.
At the end of the day, it really just boils down to these fundamental pathways. We've talked a lot about the top 3. Digital to digital for our wired Ethernet networks, digital to analog for our Wi-Fi, and analog to digital for things like voice calls. And all of them are built on those core ideas of encoding and modulation. And of course, there's always that classic analog to analog, which is the language of good old-fashioned AM/FM radio. So the next time you tap send on an email or you're watching your favorite show, just take a second to remember the incredible, lightning-fast translation that's happening just beneath the surface. This language of data is an invisible but absolutely vital foundation of our entire world. And it really makes you wonder, what other invisible languages, what other hidden systems are quietly powering everything around us every single day? Thanks for joining me.